Hey everyone, so in this video we're going to be talking about the standard normal distribution. And we touched on this in the last video, but we're going to dive in a lot deeper in this video to find out how we can calculate probabilities using the standard normal distribution. So just a review of what a normal distribution is in general. The normal distribution is symmetric and unimodal, and it kind of looks like a bell, and we call it a bell curve. And the parameters we give the distribution are a mean and a variance, and these are going to be mu and sigma squared respectively. And again, respectively, these determine the location and the spread of the distribution. The mean tells us where the distribution is, and the variance tells us how spread out the distribution is. So if x follows a normal distribution with mean mu and variance sigma squared, then we determined that we could standardize x by subtracting its mean and dividing its standard deviation, and that'll give us z. And we determined that z is then going to have a mean of 0 and a variance of 1. And what that means then is that z is going to be a standard normal random variable. And we talked about how standardizing puts everything on the same scale, but another nice perk of standardizing is that it's really easy to work with the standard normal distribution. And we'll see how we can do that in a little while. So again, this is an image of the standard normal distribution. We saw this in the last video. This is the distribution of z. It has a mean of 0, it's centered at 0, and each tick mark away, each standard deviation is going to be 1. So another thing I want to review is the empirical rule. Remember, the empirical rule said that approximately 68% of values lie within one standard deviation of the mean. And then 95 were within 2 standard deviations of the mean, and 99.7 were within 3 standard deviations of the mean. But the biggest drawback of the empirical rule is that it only works when the values are exactly 1, 2, or 3 standard deviations away from the mean. And we touched on that during the empirical rule video. So for example, we wouldn't be able to say anything about something that's 1.5 standard deviations away from the mean. And we can handle these situations in another way. So again, this is what the empirical rule looks like. 68% of the observations are within one standard deviation in either direction. 95% of the observations are within 2 standard deviations in either direction. And 99.7% of observations are within 3 standard deviations in either direction. So now what we can do to handle that issue that comes up with the empirical rule is we could actually use z to find probabilities. We know a lot about the standard normal distribution, and when we standardize x, it allows us to use what we know about the standard normal distribution to calculate probabilities. So let's look at an example. So traditional light bulb lifetimes follow a normal distribution with a mean of 1,000 hours and a standard deviation of 150 hours. So what's the probability that a light bulb lasts less than 1,210 hours? So first of all, I always recommend listing out the information that we have given to us so that if we need to use it in a formula somewhere, we have it handy. So we're told that the mean is 1,000 hours, so that's mu, so mu is going to be 1,000. We're also told that the standard deviation is going to be 150 hours. So instead of getting the variance, the standard deviation is given to us outright, which is really nice. And then the value that we're interested in is 1,210, so that's going to be x. So now our first step here is going to be to standardize this value x. So we want to subtract the mean from x, which is going to be 1,210 minus 1,000, and then we're going to want to divide that by the standard deviation. which we determined was 150. So if we do that, we'll end up getting 210 over 150, which is 1.4. So notice, since this z value is 1.4, it tells us that 1210 is 1.4 standard deviations above the mean. And since this isn't exactly 1 or exactly 2, we can't use the empirical rule to help us here. So before we calculate this probability, let's look at what's going on here. So this is our distribution of x. Remember, our mean was 1,000 and our standard deviation was 150. So every time we take a step to this next tick mark, it's going to be 150. So this is 150, and then this is another 150, which would get us to 1,300. So when we mark where 1210 is, which was the value of x we were interested in, it's going to be right here. And the probability that we're interested in is the probability that the lifetime of the light bulb is less than 1210. So we're interested in getting the area under this curve. So that's just going to be this yellow part here. So what happens when we standardize this, it puts this in units of standard deviations. So what this tells us is that this is 1.4 standard deviations or 1.4 tick marks above this mean of 0. And that's useful information because now we can use what's called a z-table to look this value up and come up with this exact probability. Because otherwise we would need to either use software or we'd have to be really, really good at calculus to be able to determine exactly what this probability is. So that's why the z-table comes in handy. So quick overview about how the z-table works. In this column, in this margin, it gives the z value up to the first decimal point. And then to fine tune it even more, we can look up the second decimal point along this row in this margin here. So since we're looking for 1.40, we can look for 1.4 and then we can look at 0. And what that will give us is a cumulative probability. And remember, a cumulative probability means the probability that z is less than or equal to 1.40, which is the probability that we were interested in. So when we look this up on the table, we get 0.9192. So in other words, there's a 91.92% chance that the light bulb lasts less than 1210 hours. So now let's look at a slightly more complicated example. So what's the probability that a light bulb lasts longer than 700 hours, meaning greater than 700 hours? So again, we can standardize this value of x. Remember, our mean was 1,000 and our standard deviation was 150. So when we standardize this value of 700, we'll end up with negative 300 over 150, which is negative 2, exactly. So what happens again when we're standardizing, we're taking this value and we're determining how many standard deviations above or below the mean it is. And it turns out that since we have a z value of negative 2, it means that this value 700 is 2 standard deviations below the mean. And since we know a lot about how to calculate the probabilities using z, we can determine the area of this yellow region that we're interested in using the table. So when we look at this on the table, again, we're going to be looking at negative 2.0 in the left margin, and then we're going to be looking for that 0.00 on the top. So when we look at that, we find negative 2 here, and we find 0.00 here. So what we come up with is 0.0228. But we have to be careful here because what we just looked up is the probability that z is less than negative 2, which in this case is this white tail right here. But what we're actually interested in is this yellow area here, which is the opposite of this white tail. Now, remember, one of the properties of these probability distributions is that the area under this entire curve is 1. So what we can do is we can take 1, which is the area under this entire curve, and then subtract off this little white tail that we just looked up in the table. And what we're going to be left with is this yellow area that we're interested in. So when we do that, we'll get 1, which was the area of the entire curve, minus the probability that z was less than -2, which was that little white tail on the left that we just looked up on the table, and we're going to get 0.9772. So in other words, the probability that the light bulb lasts longer than 700 hours is going to be 0.9772, or there's a 97.72% chance that the light bulb lasts longer than 700 hours. So notice in the last example, we could have used the empirical rule because we got z equals exactly -2. So if we had used the empirical rule, what would we have gotten? So remember, the empirical rule says that the probability that z is between -2 and 2, or within 2 standard deviations of the mean, is approximately equal to 0.95. And then from the examples that we did with the empirical rule, we determined that since there was 95% in the middle, then there was 2.5% on either side in the tails. So the probability that z is greater than 2, or the right tail, is 0.025. So what we can do is we can add those two together because we were interested in what was in the middle plus what was in the right tail. That was what the yellow area was made up of. So this is what was in the middle, and then this was what was in the right tail. So when we add those together, we'll come up with 0.975, which was pretty close to the 0.9772 that we got using the z-table. So now let's look at another example. So what's the probability that a light bulb lasts between 790 and 1240 hours? So now we're actually given two x values here. So what we need to do is we need to standardize both of them individually. So when we standardize the first x value, which was 790, we'll get -1.4. And when we standardize the second x value, which was 1240, we'll get 1.6. So when we look at what's going on here, now what we're interested in is getting the area of this yellow region in the middle. This is where 790 is, and this is where 1240 is. And we determined that they were respectively -1.4 and 1.6 standard deviations away from the mean. So if we look up these values on the z-table, we would find that the probability that z is less than -1.40 is 0.0808, and the probability that z is less than -1.6 is going to be 0.9452. But what we want is the probability that z is between those two values, or the area between those two values. So what we can do here is we can take the area that's to the left of this 1.6 here, the entire area, including this tail, and then we can subtract off the area that's to the left of this -1.4. So we're taking this whole area right here, and then we're subtracting off this little white tail right here, and what we're going to be left with is going to be this yellow region right here, which is what we're interested in. When we do that, we take the area to the left of 1.6 minus the area to the left of -1.4, which we determined were 0.9452 and 0.0808. So we're going to get 0.8644 here. So the probability that a light bulb lasts between 790 hours and 1240 hours is 0.8644, or there's an 86.44% chance that the light bulb lasts between 790 hours and 1240 hours. So now let's talk about percentiles. So we talked about percentiles a little bit when we were talking about Q1 and Q3 and the median and IQR, but let's get a little bit deeper into it because it ties in pretty closely with what we've been talking about so far in this video. So a percentile is a value such that a certain percent of the possible values of the distribution are below that value. So for example, 20% of values are below the 20th percentile, 90% of values are below the 90th percentile, and so on. Now, the other thing this means is that 30% of values are above the 70th percentile. Because if 70% of the values are below the 70th percentile, that means 30% of the values are above the 70th percentile. And like I said, we've seen this concept before. We talked about how Q1 is the 25th percentile. We talked about how the median, or Q2, is the 50th percentile. And we talked about how Q3 is the 75th percentile. So this is kind of like the flow of what we were doing earlier. We had an X value, and then we standardized it, or we converted it into Z, and then we looked up the value of Z in the table margins, and then we found the corresponding value in the body of the table, and what that gave us was a percentage or a probability. So what we were doing was we were working our way left to right on this diagram. But what if we had to go the other way around? What if we were given a probability or a percentile and we needed to work our way back to X? So for example, what if we were asked what the 10th percentile of light bulb lifetimes was? So now what we actually have is this percentage or this probability. And what we have to do is we have to work our way backwards all the way until we get back to X. So what we want is the value of X such that 10% of values are below that value. Or if you want to look at this mathematically, what we're looking for is a value B such that the probability that X is less than B is 0.1 because we're looking at the 10th percentile. So now the information that we actually have is the area of this yellow region. So what we don't know is the value that corresponds to this yellow area of zero point 0.1 or 10%. So what we need to do is we need to look up what z value gives us an area to the left of 10%. And then once we find out what this z value is, we can convert it back into x. And once we get that x value, we'll get our 10th percentile of light bulb lifetimes. So this time, what we actually have is what's in the middle of the table. We have the probability or the percentile, and what we're looking for is the z value that corresponds to it. So if we look in the middle of the table here, the closest thing to 0.1000 is going to be a z value of negative 1.2, and then the next decimal point is going to be 0.08. So it's going to be negative 1.28. So now that we have our z value, now we need to convert this back into x because we're working backwards. Remember, our formula for converting x into z was this. This is the way we standardize x. We would subtract the mean and divide by the standard deviation. And all we need to do to get an explicit expression for x to get it by itself on one side is to just rearrange this formula here. So what we can do is we can multiply by sigma on both sides and then add mu on both sides, and we're going to be left with this. X is going to be z times sigma plus mu. And when we solve for x with all the inputs that we already have, we'll have negative 1.28, which was our z value, times 150, which was our standard deviation or sigma, plus 1,000, which was our mean, mu. And what we're going to get is 808. So the 10th percentile of light bulb lifetimes is 808 hours. Or in other words, 10% of light bulbs last less than 808 hours. And that's what the 10th percentile tells us. So now we can look at another example where we're being asked what the cutoff for the top 20% of light bulb lifetimes is. So just like before, we're given a percentile, we need to find x, so we're going to be working our way backward on that diagram, just like we did in this previous example. But we're saying top 20%. So what we're actually concerned with is the 80th percentile. Remember, we were talking about how 30% of values are above the 70th percentile because 70% of the values are below it. Similarly, 20% of the values, the top 20%, are above the 80th percentile because 80% of the values are below it. So what we're actually trying to find is the 80th percentile. So again, what we have is the yellow area here. We actually have that given to us. And this area is going to be 20%. It's going to be 0.2000. And on the left is the 80%. So we're looking for the 80th percentile. And we don't know what value of z that is, but once we find it, again, all we need to do is convert it back to x, and we'll have our 80th percentile. And our 80th percentile is going to be the cutoff for the top 20% of the values. So just like before, we have to find 0.8000 in the body of the table and then find the value of z in the margins that corresponds to it. So when we find that value, the closest one that's going to be to it is going to be this 0.7995. That's the closest we can get using the table. And when we do that, we'll find a z value of 0.84. So z is going to be 0.84. So now all we need to do is convert this back into x, and we'll have our cutoff for the top 20% of light bulb lifetimes. So this is the same formula as before when we rearrange the standardization formula. So this is going to be z, which is 0.84, times sigma, which is 150, plus mu, which is 1,000. And then we're going to get 1126 out of that. So what this tells us is that the 80th percentile for light bulb lifetimes is 1126 hours. So that means the cutoff for the top 20% of light bulb lifetimes is 1126 hours. So anyway, that's the end of this video. I know this was a lot and this was a big step, but if you were able to follow everything that was covered in this video, that's fantastic. If not, I wouldn't worry too much. But either way, I hope you found this video helpful and enjoyable, and I will see you in the next video. Take care.